what I want to do is look at some of the multiple choice and kind of break that down and just kind of figure out how to read the multiple choice, because all of y'all were just whining when you left here about the multiple choice. Okay? So let's really kind of focus and break this down into how do we look at, read the multiple choice to kind of help make it, more doable, or how do I know what to do? Okay? Now, you got to realize there's 32 people that took this test in this class. Okay? So when I give numbers on how many missed, when we go down through, first off, just number one. Which of the following does not behave as an electrolyte when dissolved? How do you know the answer to that one, Joshua? Has to be ionic, and it has to be soluble, right? Which means separated in the solution. How do you know? Somebody else tell me. How do you know if it's ionic? Starts with a metal. Okay? So if it's covalent, what's the only type of covalent substance that acts as an electrolyte? That would still be ammonium. It's still going to be ionic. The only type of covalent substance that's going to act as an electrolyte. What are three types of electrolytes? Soluble salts, strong acids, strong bases. Strong bases are going to be the alkali metals, and then strontium and barium, and those are all metals, so what type of compounds are they going to be? Ionic still. It's just a special type of ionic where hydroxide is the ion. Okay? So that only leaves acids. Acids are hydrogen, sulfur, and oxygen, hydrogen and chlorine and oxygen. So they're really covalent compounds that just break apart into ions, break into the H plus and the anion in water. So it's the only covalent compound that actually ionizes in water. The rest of them dissolve as how? How do they dissolve? As neutral molecules. Okay? And we're going to get into that, and we need to talk about the dissolving process itself just a little bit more. So, that's the first thing there. Now, a small number missed that one. Now, 6 people missed this one. In general, if there are weak attractions, and if you want, you can be putting corrections down as we go on this, because we are going to do corrections, but don't jump ahead. Really, don't try to get the I got to get it done mentality. We got time to get it done. I'm not rushing today. Okay? Listen and think about and contemplate what we're talking about on your answer. I promise you, if you'll just stop and listen rather than trying to get it done, it'll be way more efficient and way more productive of an experience. Because the ultimate goal here is, yes, to make an A or whatever, but it really is to learn. Okay? That's the ultimate goal. So we can use this and kind of try and figure out, okay, well, I messed up because of this, let's fix it. In general, if there are weak attractions between solute and solvent, so what step in the dissolving process is that? Which is 1, 2, or 3? So that's number 3, right? It's the last one. It's the most important one. Because that's the one that causes the other 2 to occur. Okay? If there's no attraction between solute and solvent, then solute and solute aren't going to break apart, and solvent aren't going to break apart. Which is the whole premise of the free response question between aniline and toluene. Okay? Is the whole point of, is there an attraction between the solute and solvent? Is there enough of an attraction there? And what is the attraction to break the solute apart and the solvent apart? So, if there's a weak attraction between solute and solvent, what does that mean? Is it going to be soluble or probably not soluble? Probably not very soluble. Okay? So whichever answer says that, the easier it is to overcome solute to solute. Well, what's wrong with that statement? If there are weak attractions between solute and solvent, how would you make A correct? The harder it is to overcome. The solute will be significantly soluble in what? How would we make that one true? Significantly less soluble, or not very soluble, The solute will not be soluble because it cannot overcome the solvent-to-solvent attractions. That's the correct answer. And then the more effect pressure will have on solubility. What effect does pressure have generally on? Very little on solids and liquids. It only affects gases, but it has nothing to do with the attractions. It has to do with just forcing the gas into the liquid. Okay? So, what are the solvent-to-solvent attractions in water? And you might want to just put a note on the quiz after the side of this. What are the solvent-to-solvent attractions in water? And when water is the solvent, it's hydrogen bonds. But if it has hydrogen bonds, what does that mean? It's got them all. But hydrogen bonds are the strongest of the three and the most significant of the three. Okay? So you have to be able to overcome those strong hydrogen bonds. So there has to be a strong enough solute-to-solvent attraction to overcome those solvent-to-solvent bonds, double hydrogen bonds in water. Again, make note of that for the short answer question between toluene and aniline, because it's all about that. All right, now, again, the math here. Most of y'all did the math right on this. What volume of 2 molar HCl is needed to obtain 2.92 grams of HCl from the solution? Somebody tell me, how do we do that? Molar mass of HCl, which is of HCl, which is 36.5 grams per mole. Then what? Okay. 2.9 something what? Grams divided by 36.5 grams per mole. That's going to be over liters is equal to what? So how, mathematically, just real quickly, what's going to happen to these two numbers in the equation? They're just going to swap, right? So the reality is it's going to be liters is going to be 2.92 divided by 36.5 divided by 2. And that comes out to? Okay? You got to multiply by anything.
No, you have to do milliliters.
Okay, so that's, okay, so yeah, not molar, that's liters. Good job, Steve. Okay, so that's going to be times 1,000, so it's 40 milliliters. That's just plugging into the molar. How do I know that that's not a stoichiometry problem? Well, you're not following me.
You don't have like a remote.
Did this turn off?
There's no reaction.
Is this not on? Great. Where I just put it. Okay, so number 4 is the same thing. Number 4 is you just calculate the molarity. Now number 4 is the exact same problem as the first problem on the last page. Okay? When you look at that last problem, they want actually, I think it's the first problem on the last page where the calcium chlorate breaks apart. You calculate the molarity. Then what do you have to do? What does calcium chloride, CaCl2, break up into? Ca and 2Cl, so you have to multiply the Cl times 2. So notice the math is very simple. It's 222 divided by 111 is 2. Divided by 1,000 milliliters is how many liters? 1 liter. So the concentration of the calcium chloride is 2. So the calcium ion is going to be 2. The chloride ion is going to be 4. Okay? Now, number 5. Okay? Number 5. Remember, 32 people took this, 21 missed it. Okay? I think there's some random guessing involved in there as well. What volume of water must be added to 10 milliliters of 6 molar HCl to make a 1 molar solution. So what type of problem is this? Dilution problem, right? Okay? So we get a dilution problem, which is going to be MC BC is equal to MD BD. So we end up having the concentrated is equal to 10 milliliters of 6 molar. And we want to make 1 molar. BD. So obviously we divide by 1, and so the answer is going to come out to 60 milliliters. Well, why did I get it wrong? Because it says what volume of water must be added. So you started with 10 milliliters. So to get to 60, how much water do you have to add? Okay. Now, the only reason I put this on here because this is an AP question. Okay. I thought it was cheap because everybody knew how to do it. It was a purposeful distractor or whatever. But notice the word added. On another year, they just said, well, they just made you just do it. What's the total volume? So you have to just read the question carefully as to what it's looking for. Okay? So 60 is the total volume, but you started with 10, so you're only going to add 50 milliliters of water. That's one of that's 2 of the reasons you got 4 points back. Okay? That's 2 out of your 4s because that one I just feel is tricky. I wanted to put it on there just to expose you to it, okay, and make you read critically, but. All right, number 6. Number 6, 12 people still missed this one, and I was kind of disappointed the number of people that missed this one. 13 people actually. Given the following equilibrium system, and given that with energy on the right-hand side, is this an endothermic or an exothermic reaction? Exo. So you might want to put that right down in there. This is exothermic. Okay? So that's the first thing we look at. Where's energy on this? What effect will raising the temperature? So temperature now is on. So here's we're in balance. But heat, for you guys, the energy is over here on this side. This is your delta H, your energy. So when you add heat now, heat jumps on the teeter-totter over here, the seesaw. Okay? So which way does the reaction have to go? This way. What happens to the solute and the solvent on this side? There's a plus sign in between them now, right? Which means they're 2 separate terms, which means they separate from one another. So what happens to the solubility? It decreases. Okay? What's an example of something that is exothermic like this? What type of solute has a negative heat of solution? What did you say? Strong acid. H2SO4 is one. What else? What's your whole group of substances have? All of them have negative heat of solution. You guys know this. What type of elements, should I say, all have a negative heat of solution? Really? We're not remembering this at all? Gases? All gases have a negative heat of solution. You increase the temperature on gases in solution, the solubility always decreases. Okay? Well, as I was saying, class of elements, group of elements. I mean, I didn't know how to phrase it other than that. Oh, well, that's this one. That's what I'm saying. What's another example of this one, though? That's what I was just asking. So, strong acids get very hot when you dissolve them. Okay? So they're very exothermic. And gases. Now, gases, they're not going to have a big temperature change. That means that the magnitude of their delta H is going to be pretty slow. It's going to be pretty close to 0. All right. Now, number 7. Most of y'all got number 7. Okay? There was some that missed it. But which of the following would be least soluble? So how do you know this? Least soluble. Alex.
With the pool, the electrons between the
Okay? With a pull, the attraction between solute and solvent, but what's a quick, easy way to look at it? Hydrocarbons are nonpolar. So what's the difference then between these molecules? They all start adding OHs. What can water do with an OH? What type of bond? Can form hydrogen bonds, which makes a really strong solute to solvent attraction. If there's a strong solute to solvent attraction, it's going to dissolve. Okay? Whereas, if you look, so the answer is D. Okay? Because it is a hydrocarbon, so it is polar or nonpolar. So what's the only type of attractive force there? What? London forces. It's the only type of attraction between nonpolars, London. Is that strong or weak? Weak. So water's only going to be attracted to the... Anybody want to guess the name of that one? Decane. Because it's 10. Decane. Okay? Water's only going to be attracted to that by the weak London forces. So those attractive, the solute to solvent attractions are not strong enough to overcome the much stronger hydrogen bond attractions between the water molecules themselves. Therefore, it won't dissolve. The water's not going to move apart to let the decane in. Again, think about that when we go to the short answer question. Now, number 8 was the second most highly missed question. It actually tied. Tied number 5. 21. And this is the one we just said. The temperature, as the temperature increases, the solubility of a gas in water, what do we know about this delta H of a gas in water? It's negative. So if you increase the temperature, what happens to the solubility? It decreases because the dissolution of the gas in water is exothermic. Dissolution, what's that? That's a fancy word for? Dissolving.
See, I circled A.
Now, we haven't talked about entropy at all. Does anybody even remember what or know what entropy is? That's enthalpy. Anybody know what entropy is? Hey, let me give you a clue. Now, this isn't necessarily true on the actual AP test when you take it, but on my unit test, if you haven't seen the word, it's probably not the answer. Okay? Now, on the AP test, it's a whole new set of rules there because there's probably stuff on there they're going to put on there you haven't seen. I try to do my best to cover it, but there's always at least one thing in there. I say, oh, crud, I didn't cover that one.
Could you put like increasing on a few of those so I can knock them out?
Oh, yeah.
That would be nice.
Yeah, then I'm like, oh, okay.
Okay, but look at D. Decreases regardless of whether the dissolution of the gas is exothermic or endothermic. What did our equation say always? We always have heat on some side, right? So temperature always affects.
But that was a good answer.
Okay? Temperature is always going to have an effect. It's going to push the equilibrium one way or the other. It's either going to be on the left side of its endo or on the right side of exo. Now, the closer it is to 0, the less effect temperature is going to have, but it's still going to have an effect. All right. So we need to know gases have a negative heat of solution. Gases are less soluble as you increase the temperature. You put a can of soda out in the sun, it goes flat. The CO2 comes out. Number 9, significant number. Under which of the following conditions could the most CO2 gas be dissolved in water? Again, the two factors that affect solubility are temperature and pressure. So what did we just say for a gas? Is it going to be more soluble in high temperature or low temperature? Low temperature, because as temperature increases, the solubility decreases. So low temperature, and what about pressure? You want high pressure. That's why, again, they put the fizz and pop. They keep it under pressure. So for gases to be soluble, you want low temperature, high pressure. Keep the lid on, put it in the fridge. All right, then we go to number 10. 11 people, which is a third. What does a saturated solution? So that's the first thing when you're reading this. A saturated solution. What does that mean?
You dissolve as much as you can.
You've dissolved as much as you can. It's maxed out. The sponge is saturated. It can't hold any more water. Okay? So if you need to, put a note there. Saturated means full. So if you put another grain of salt in, what's it going to do? It's just going to sink to the bottom. Now, why isn't it going to cause more to precipitate out? That's only supersaturated. Why doesn't adding one more grain make it go supersaturated? That cool down thing. You don't just make a supersaturated solution. The whole point of saturation is the maximum amount that can go in. Supersaturated, number one, are rare. Well, I mean, I'm not confused even what day it is today, so I was going to say, what time? Do we have lunch? When's our break? We don't have a break. Okay?
We have lunch right now.
Yeah. Okay? So saturated means full. So normally, if you just put more in, that's just going to sit at the bottom. Okay? All right. So adding more doesn't make supersaturated. The only way to make supersaturated is make a saturated solution at a high temperature and then it cools slowly, and it might go supersaturated. Probably not. I keep wanting to just skip over some, and we keep missing. 11 people missed number 11. Okay? Now, breaking up into particles. This is really like our net ionic equation. What is calcium chloride? What's it going to break up into? Number 11.
I missed 11.
CA. So how many particles are we going to get? 3. When ammonium sulfite. What's that going to dissociate into? 2 NH4 pluses plus an SO3, 2 minus. So how many particles we get? 3. NH4Cl. What's that going to dissociate into? NH4 plus Cl minus. Okay, so when ionic compounds dissolve, they dissolve as ions. They dissociate into ions. This is asking which one's going to break up into the most particles. How many particles we're going to get? And that's important for this thing called colligative properties. You guys did it last year, the freezing point depression. Because the more particles you get, the more the freezing point is going to go down. And then sodium phosphate, Na3PO4. What's that going to break up into? 3 Na pluses plus
PO4.
just the PO4. This is why we have to know our ions also. So how many? We got 2 here. How many are we going to get there? 4. And then the last one is C2H5OH. So what type of compound is that?
C3H.
C3H5? Is it really?
Yeah.
It doesn't exist, but it should be a C2. But it's an alcohol. Now, how do I know it's not a base?
Because base is bonded to a metal.
Base is bonded to a metal. How do I know it's not an oxyacid, Jen? How do I know it's not an oxyacid? Oxyacids are OHs bonded to nonmetals because it's bonded to carbon. When it's OH is bonded to carbon, it's an alcohol. So what type of substance does this make it? An alcohol. So is it an ionic substance? Is it an electrolyte? It's a non-electrolyte. So how many particles does it break up into? 1. It dissolves as a neutral molecule. So it goes to C3H5OH. So we only get 1. Okay? So when we talk about colligative properties, freezing point and boiling point, freezing point depression, boiling point elevation from last year, you have to know how many particles. They always talked about a certain non-electrolyte was dissolved because that just tells you that it only gets 1 particle. So what's the answer to this one? Sodium phosphate, because you get 4 particles. Now, just out of curiosity, what was the challenge on that one? Okay? Okay, now how would we know they're all soluble? Alkali metal, ammonium, ammonium. Now, this one, first off, the chart's up there, but what are the only halides that are insoluble? The two most important ones. Lead and silver. Okay? Lead and silver. All other chlorides, all other halides are soluble. Okay? But, again, which of the following produces the greatest number of particles dissolved when 1 mole of substance is dissolved in water? So, but Isaac, when you read that, when it's dissolved in water, you can assume it's dissolving. Okay? Based upon the way the question's worded. So we really didn't even have to know the solubility. You can assume based upon that, as they're saying, when it's dissolved, in water. It doesn't say if it's dissolved in water or if it dissolves in water. 12. If you have highly exothermic heat of solution, which is bigger? Lattice energy, energy of hydration? Energy of hydration.
How come it said it had a high, it said solid solute instead of solid,
Because that probably is a wrong answer.
No, I'm saying, if the question asks which of the following is probably true for a solid solute, wouldn't it just...
For a solid solute, so in other words, a solid that's being dissolved, a solid solute that is being dissolved, like sugar or salt or something like that. Okay? So it's going to have, if it's highly exothermic, what does that mean about its lattice energy? What's wrong with A? How do we make A true? It's going to have a low lattice energy because the energy of hydration is going to be higher. The solute dissolves, the temperature of the solution decreases. If it's highly exothermic, what's going to happen to the solution? It's going to increase. Now, a lot of people were asking me, is this the solution? Is this the surroundings? Whatever. When you put it in, when you put sugar into water, okay, the whole thing is now the solution. The whole thing's either going to get hot or cold. Okay? Now, there are the chemicals on the inside, the small part that's the actual system that's changing its potential energy. But the whole thing, you're not going to have the system and the solution is kind of like a little subset. When you put it in, the solution gets cold. That's the whole thing. That means it's endothermic. If the solution gets hot, it's exothermic. Don't try and break. There's the energy change going on between kinetic and potential that we talked about, but don't try to overthink that. The solution is the whole thing. It's really the solution is considered the surroundings, I guess, and make it easier. Now, 13 is Coulomb's law, and what are the two answers that are right?
C and D.
C and D. Okay? What's wrong with A? Do larger ions have stronger Coulombic attractions? No, smaller ones do, right? Okay? And the electronegativity has nothing to do with it. Okay, now number 14. 10 people missed. So again, there's another third. Okay?
I know why. And I hate myself.
All right. Well, that's it. As long as you can figure it out, that's the important thing. What is wrong with statement number 1?
That's partly true. That's why it's
Solvation. What is solvation? Is it solvent?
It's the solvent surrounding the solute.
It's the solute attaching to, the solvent attaching to the solute. But it's the attraction between the solute and the solvent that causes solvent. There's 3 steps. There's 3 steps. Okay? Step 1 is solute. Step 2 is solvent. Step 3 is solvent.
So salvation is the attraction.
Salvation is there would be an attraction between the solute and the solvent.
Can you explain a little bit more? I still understand this.
Okay? Because salvation, the attraction between solute and solvent, is what causes the solvent to move apart in the first place. Solvation is the attraction between the solvent and the solute. Yes, y'all listen, the solvent does have to move apart. But the solvent moving apart isn't the process of salvation. The process of salvation is when the solvent attaches to the solute, pulls it into solution, which then causes the solvent to move apart. Okay? So, salvation is solute solvent. It's the third step of the process. Now they're really all happening simultaneously, but we're breaking it up into 3 steps. And then 15, most of y'all got right. It's a 3-step process. Okay. Now, most of y'all, because we practiced it and did so much, most of y'all did pretty well on number 1. If you messed up on number 1, get with someone and learn how to draw it right. I made a lot of notes. One thing, on number 1, real important. A lot of y'all put the water, you put the negative sign on the oxygen and you put a positive sign on the hydrogens. Okay? Water isn't an ionic compound. It's a covalent compound, so don't put charges. Now, one person, but I think it was in the other class, used the delta symbol, the delta positive and delta negative. That's okay. That shows partial positive, but if you put positive and negative, it's going to make it look like it's an ion, and so it's going to be wrong. So just put the water. Don't put the charges on there. If you put the hydrogens on the right, connected to the negative, and the oxygen on the positive, that's all you need to do. Don't put the charges. All right. Number 2 is going to be it. And once I get number 2 done. All right. Mallory, I put very good answer on yours. Did I put a whole bunch of words out? Did I add to it? Did I edit it? Okay. I want yours.
Good job, I just got right on here. Shut up.
Okay, this is real important because most of y'all had kind of the idea.
Okay, I think it's because you said over here. This is true.
I think I said like the only reason I did this is because solvent is trial and I didn't do much of that. I just saw solvent solvent. It took like 1 year and 2 years and that's the real answer.
No, it's not all. It's all. Okay.
Okay. Now, when we look at molecules, they're complicated. We've never seen them before. Kind of get a little intimidated by looking at it. All right? That is all multicolored. Let's see if that helps at all. Not really. Sorry, guys. But when we look at this, if this something is going to be soluble, it's got to have that solute to solvent attraction. Okay? Now, when you look here, the one thing that's different between the 2 molecules is this. Okay? Now, this nitrogen is attached with a hydrogen to it. Since it's phone, F-O-N, what does that mean it can form? Hydrogen bonds. Now let me ask you this. Is this bond right here a hydrogen bond?
No.
It is not. Where do hydrogen bonds form? Okay? Between molecules. It's an IMF. Okay, this is incredibly important. Intermolecular force. What does the prefix inter mean? Between molecules. This is a covalent bond. This is a covalent. These are all covalent bonds. When something dissolves, if you dissolve aniline in water, do any of these covalent bonds break? So what is breaking apart from what when it dissolves? Nitrogen breaks away from the carbon?
No, the hydrogen.
This molecule here breaks apart from another identical molecule, another aniline. The aniline molecules are breaking apart from one another. Okay? The IMFs are intermolecular forces, forces between molecules. So when this is dissolving, the water is not breaking any part of this molecule apart. It's breaking this aniline molecule from another aniline molecule from another aniline molecule. So aniline is a solid. You buy it, it's like a real white flaky powder. So it's a solid, meaning that all of these molecules are stuck together, billions of them all at one time, to form something big enough for us to see. And then you put it into water, and the water breaks each of those molecules apart from one another. It's breaking the intermolecular forces, the forces between molecules. Now, because it has this NH2, it can form hydrogen bonds with itself. Another one of these comes along. And this is the other two reasons, okay? Because I know that there's still a lot of confusion on this. And so I took some of the blame for this one. So when another aniline comes along, it kind of flips over. You can have this nitrogen part with its two hydrogens, and then all of this, and it's really just a benzene ring. Yeah, it's just a benzene ring. We'll just shorten it up like this. So we're going to have this attraction right there with another aniline. This is the hydrogen bond. So then another one can come over and do the same thing here. You can have another aniline coming over and attaching here with this nitrogen, hydrogen, hydrogen, benzene ring. Have another hydrogen bond forming there. And so they can just keep attaching to one another all around at that spot. So you have the solid, the aniline, the flake of aniline crystals, all bonded to each other with these IMFs. And then you put it into water. Well, now the water is going to come in. Well, the water can also form a hydrogen bond. Because this is extremely positive, this is extremely negative, and they attract to one another. So the water comes in and starts attacking all the different hydrogens and all these different points, and it can actually pull it into solution because it has a strong solute-to-solvent attraction because it can form hydrogen bonds with the aniline molecule. So aniline can form hydrogen bonds with itself between the molecules, and then the water comes and begins ripping the aniline molecules apart because it can form a hydrogen bond with it, a very strong solute-to-solvent attraction. Okay? Now, what does this have? Nothing. No poles. It's hydrocarbon, totally non-polar. Okay? So what's the only type of attractive force between itself? London forces. But what does water have down here? When it goes and gets put into the water. Water is attracted to itself. With hydrogen bonds. So water is very strongly attracted to itself. Water has no attraction to the toluene. So there's the solute-to-solvent attraction is too weak to overcome the much stronger solvent-to-solvent attractions, the hydrogen bonds between the water. So as a result, they just don't mix. There has to be this attraction here. Because water has the ability to form a hydrogen bond, because of this, there's a strong solute-to-solvent attraction that's great enough to overcome the solute-to-solute attractions and the solvent-to-solvent attractions. Therefore, it dissolves. In this one, there's only weak solute-to-solvent attractions, which are not strong enough to overcome the much stronger hydrogen bonds between the water molecules. Therefore, it does not dissolve. Now, let's put that into words. And I strongly recommend you copy this exactly. This is the answer for any time you have one thing that's soluble and another thing that's not. That helped it a little bit, didn't it? Toluene has limited solubility because it is nonpolar, which means it only has London forces holding it together with other toluene molecules. And you might want to add in here to overcome the dipole-dipole and hydrogen bond, dipole-dipole attractions and hydrogen bonds between water molecules. Catherine, I want to put yours up there too in a second. Aniline is polar, which means it has strong dipole-dipole attractions. These dipole attractions between water and aniline are strong enough to overcome the dipole-dipole attractions and hydrogen bonds between water molecules, and the dipole-dipole attractions and hydrogen bonds between aniline molecules. So the key is you're talking about the differences between the attractions of solute to solvent attractions compared to the solute-solute and solvent-solvent. For some reason it won't darken up.
Hey, I wrote it down outside. Good job.
So
I wrote it down and I started laughing at myself. Like, why did I write that?
I don't even know what you're saying. It can't, that's not that's not comprehensive.
So do we have, does everybody have that?
No.
Golly.
It's long. We don't write as fast as you talk. I ain't shorthand. I'm gonna get all these corrections right in detail, so we know.
You're going to see these questions again next week.
Is that everyone?
No, but same concept. Hey, you're almost going to have, hey, you're basically going to have to write the same answers.
So it's saying like that aniline has dipole-dipole.
Yes. Yes. So they're attracted to each other themselves, and they're attracted to each other. But the attraction, because there's a strong solute to solvent attraction, the water to aniline,
How do you know that?
because it has the ability to form hydrogen bonds. If you can form hydrogen bonds between the solute and the solvent, they will dissolve.
Okay, where did you put?
And the reality is right up in here, it needs to really kind of probably say the attractions between the solute and solvent. Okay, which I'm going to show you Catherine's, and that's going to be.
Well, if I didn't put that, will I still get
No, you're going to be fine. But again, we're thinking about the concept. The main concept is there has to be an attraction between the solute and the solvent for them to dissolve. Okay? So we look at where is there going to be an attraction. Almost always that attraction is going to be a hydrogen bond. It doesn't have to be. It could be just dipole-dipole attractions. It could be polar to polar. But almost always in these problems, they put something in there where it's going to be a hydrogen bond attraction. Whereas a nonpolar, when you have a nonpolar, there's not a strong enough a solute to solvent attraction to overcome the hydrogen bonds in water between water molecules.
We're writing this next for
Toluene has limited solubility because it is nonpolar, which means it only has weak London force holding it together with other toluene molecules. And if you wanted to, you could put here and 2 water molecules. These weak London forces are not strong enough to overcome. So it's attracted to these toluene molecules, and it's attracted to the water molecules as well, with London forces only.
So we couldn't try to
You say,
have an attraction between.
right, so if I was to maybe even modify this a little bit, so toluene is limited because it is nonpolar, which means it only has weak London forces attracting it to the water. These London forces are not strong enough to overcome the dipole-dipole attractions and hydrogen bonds between water molecules. That's probably how I would have written it. Okay? Over. My comment on Catherine's was, ooh, this is too detailed.
This is too.
Oh,
Nice, Catherine.
Okay? So this says, aniline contains a nitrogen, which is extremely electronegative. Although it forms covalent bonds with the hydrogens bonded to it, the electrons tend to gravitate towards the nitrogen. The offset of electrons cause the hydrogen to have a slightly more positive charge due to exposed proton nucleus. Okay? The dipole-dipole forces created by the nitrogen and the hydrogen is enough to form a solute to solvent. Now this is really where it really kind of needs to start. That's all in explaining of what causes a hydrogen bond or why it is, but you really don't need to say all of that. You don't have to explain all the electronegativity and all that. Now notice how she did put here that she has the hydrogen bond being formed and then the water kind of coming in. Okay? So, the dipole-dipole forces created by the nitrogen and hydrogen is enough to form a solute to solvent attraction to the polar water molecules that is stronger than the solute or solvent attractions, allowing the aniline to dissolve. That's the key point right there. Toluene, on the other hand, has a carbon instead of a nitrogen. Carbon is not as electronegative as nitrogen and thus does not create enough dipole-dipole force to overcome the solute and the solvent attraction. Because it cannot create strong dipole attraction with water, toluene is not soluble. Because it doesn't have a solute to solvent attraction, it's not soluble. And the only thing you could add in there is says it does not, because it cannot create a strong dipole-dipole or hydrogen bond with water, toluene is not soluble. See, up here, then she put this added in. Non-polar, therefore London forces between toluene molecules, not strong enough to overcome the dipole-dipole bonds in water. Okay? And then here she's showing the water forming the hydrogen bonds. This part right here is almost all the, this right here in diagram form is pretty much the answer. The concept, the whole point, wording, we can work on wording as long as you understand what you're trying to say. They've got to be attractive. Okay? Now, last thing I'm going to say about B, you have to just learn. If you're not figuring out, if the whole idea of exothermic, endothermic is still struggling, memorize and worry about trying to understand it later. Okay? If the solution gets cold, if you put something in to water and everything gets cold, Is that an endothermic or an exothermic reaction? Endo. Don't think about anything else. You put something in, it gets cold, it's endothermic. So what's the sign of delta H? Positive.
It's opposite.
Okay? Because it's the difference between y'all. It's the difference between potential energy and kinetic energy. Kinetic energy of the surroundings is being used to go into, to enter into the system, the dissolving process to break bonds, to make the solute separate, to make the solvent separate. But temperature doesn't measure that. That's a potential energy. So the kinetic energy of the water and the surroundings, everything that the reaction is taking place in, is being changed to potential energy. We're looking at the temperature of the surroundings. The surroundings got cold, so energy left the surroundings and entered the system. The system is gaining its potential, which is latent heat or hidden to the thermometer. And then when paper burns, energy is leaving, exiting, going to the surroundings, so the surroundings get hot, but the ashes themselves have less potential energy than they did as a paper. It's potential versus kinetic changing. But again, if it's not making sense, memorize it. I promise as life goes on, it'll make more sense. All right, then if you missed, so you need to rewrite all your short answers and then resolve the problem if you missed any part of the problem.
On all three.
Just right.
On all, okay, so all three.
I don't know. You heard my kindergarten logic. I don't know.
No, the answer. To the front.
I know, I agree.
Okay, I need someone to explain this.
Especially
Wait, so you understood this?
the one participating in C, you only have to do the one part that exists.
So I have to read you two, this one. Why else did you have it done?
I just think you need it more.
That's what I thought. And now I have to clear, how do we manipulate, say,
Only as accurate. Corrections to the front. Details, not really details. You got to pay attention to the details.
I did it on my notes, I put it in the blank.
Not mine. No, you have your own.
Let's
I
make
don't
fun.
want it out.
I built that last night.
Hey, remind me to read some of the statements. Repeal. Well, you did it, so obviously it is. What'd you say? What'd you say? What'd you say? Well, you did it, so you So what'd you say? Alright, explain that. How would I write that? Max, you broke my little statement. That means that. I didn't know.
Okay.
How are you explaining like this? Like this.
Oh, Anthony, you can get your paper on.
Like this.
Tape, I forgot that from my dad.
I don't understand. Like I was listening to you and I still don't understand.
Okay.
Like I don't understand this. Like I know why it's not A or D.
I Okay. In order for a solid to dissolve, it has to be an attraction between the solid and solid. The stronger the attraction, the more soluble it's going to be. So if it has a weak attraction,
Can you try to
solid
put
is
testing on me?
soluble or insoluble.
How do I tell that?
Okay? In order for there to be in order for something to be soluble, there has to be an attraction between the solute and the solvent. The stronger the attraction, the more soluble. The weaker the attraction, the less soluble. That's the explanation.
About this.
Now this one, you know, how much is that?
Okay, yeah, that was my kindergarten logic, that 1 plus 5 is 6.
Oh, yeah, okay, so you need to write some people
No, this one,
I know, I'm just saying on this one.
and this one. I was like, those are soluble, so it's probably more soluble than that. 3 is bigger than 1 and 2, so that's probably the same. I really do not know how much I'm doing. Like, I'm freaking out because I'm barely having any.
You might want to stop reading, stop getting on your phone. Stop
We're talking about this.
I do mine big, like you guys' entire page. I made a very clear which one I read.
Rob, is this your restroom?
Yes, this is solid. Okay? Now, so we know here that gas is this. Exothermal. Okay? So solubility, if we increase the temperature, solubility is going to decrease. Okay? Because exothermal. Because Sally says that if you put stress,
Yeah, I got that one. I want to see, like, I thought it was just a rule. Gas temperature went up, so I put it down.
because it fits into this equation, negative delta H. Go back and look at your notes.
You guessed it.
They all are negative delta H.
This felt like, oh my gosh. This feels like, that's not what I need. Did you kill yourself? He died.
Okay?
I think that mine are better than
And then on this one, still fighting on that, but salvation is.
That's why I got it wrong. I was like, well, technically that has to happen. But that's not.
I know, but technically they all have that. All you are saying is
Energy goes into it's taking energy away from the soul.
Johnny, we're like ever. I don't know what to say. It's going to
energy that breaks apart the soul. So if it's getting cold, that means like it needs more like lattice activity. Like the amount of energy needed to break the lattice activity is greater than the energy that is created when the solute solvent when the solute energy is created. The lattice energy is greater than the outside solution. I'm not supposed to.
And then the other girl was playing such short. I didn't finish. I did like half. But then there's that other girl short. You could just play into that. You just sit right on. She's like,
He says that to me and I don't know.
well, I hate that. No, he's out of
But he's the one that he can't be touched. I guess. Stop. Really good.
Okay, do you know how dumb that is?
I don't understand.
Do you know how
what
drastic you
you're
are?
saying. I don't understand what you're saying.
I didn't point to you there.
Okay, well, I don't know how to tell you how good your wedding is. Okay, you can't. Your mom's not bad. Okay, you have those that. You have like kids like that.
There's only like really two like shares that I heard. I'm pretty sure you did.
Are they freaking out? He said SB. I thought it was really good.
It doesn't have to be. So I didn't know.
So is it your mom's
Well, why would it be your mom's sweet?
I don't know. Your mom something every single time. It's so pretty.
I missed it because I wrote down the point 4.45. I didn't think. I wrote down point 4.55. I mean, I wrote down point 4.45. Yeah, I did.
That was funny. That's really like, I was really funny. I know. I guess you didn't see like everyone was
It's only got off when you go like,
when you get down.
well, actually you did. I did the work right. I did this work right.
And now you see her question.
Yeah, but that was, we just copied the number from the problem. Yeah. Alright, Scott.
Does it have anything about me? You just lied to me.
Good.
Wait, you haven't read that.
I was like, you know,
Wait, are you talking? Are you laughing at her?
remember he said, like he said you have, it was like, you know, our call logs.
Yeah, K, N plus.
So yeah, what I remember is, like if you have 3 up here, like grand plus, 3 over 1. It's like 3 divided by 1 is 3, 1 divided by 1. So that's what I knew it is. So what AL3 had to do. And if it's a large
No, I'll let you guys do.
That's why the larger atoms, like it's hard to have a large atom. The bigger the atom, the bigger the atom, the less the attraction to the electrons, protons are slow. Protons,
would be 1 divided by 10.
No, but I
That's obvious.
Oh, wait.
I didn't do it. I just used the
That's how I told you.
For me, I just said that, okay, larger ions have a stronger magnetic attraction to ions. That has nothing to do with the
I know.
I think the smaller ions are more like
I think he was trying to say that it, I think he just forgot the word. I don't think it's funny. I think he meant to say solvation or solving or solvent when you're breaking it apart, but it's just wrong. That's just me.
You don't have to catch the season.
presence of the nitrogen.
I just got everybody.
Which allows it to
I'm
be
gonna
strong.
which is about
You have to learn how to do it.
and that came in late, so even if like
I'm talking Alex. This is what I did. Thank you. They forgot for like 2 years. I'm not really sure. Oh, you just brought around the line. Watch it go around the line.
I can't get this man.
Because of the strong attraction between the
Yeah, push it more like here. It's gonna feel a little bit awkward. It's not gonna be really big. Don't push it like that. Put a little bit of that.
Even at higher strength.
Now that's what it is.
Because the compressed water can help with one molecule. Okay, if you're finished, when you're finished, staple the corrections to the front.
Wait, I have a quick question. No, I didn't say that I did that. This is
Okay, so
All three things happen.
yeah.
that means
Solid,
that
that's break apart. Solid, that's break apart. Solute and solvent attach. Solvation is only the solid and solvent attaches. Yes, that does cause the solvation.
Hey, could you write the equation? Not write the equation. Do that.
I'll give it to you guys.
The solvation is when solute and solvent attach. It's not the solvents break apart. It causes the solvents break apart, but it's not the process of the solvents.
It's greater than 3.
Toast like this,
So here, that's the same thing. Solute, always
Okay. Given these molecules here, which one actually shows hydrogen bonds? In the diagram above, which of the labeled arrows identifies hydrogen bonding in water? Okay? I heard. What type of bond is A? That's a covalent bond. That's an intra, within the molecule, intramolecular bond. It's a covalent bond. Okay? What's wrong with B?
B, oxygen bonds.
Because it's negative attracted to negative, right? What's wrong with C? Positive to positive. Okay? So, these aren't attractions. So here, this is the hydrogen bond. Now, how does the strength of A compare to the strength of D?
D is stronger.
A is a lot stronger. It's a covalent.
Remember, kindergartners versus adults. Okay? The intermolecular forces are the weak ones. Now, hydrogen bonds are the strongest kindergartner, strongest of your 3 intermolecular forces, but it's still weak compared to this. So when you go and you boil water, and you see the steam coming off. What's the formula of the components of steam? What is steam still? Still H2O, right? So which bond did we break, A or D, when you boil water? D, because it's the much weaker bond. It's the one you got to get water super, super hot to be able to break the covalent bonds, make it decompose into hydrogen and oxygen. It doesn't do that, but boiling water isn't breaking it into hydrogen and oxygen. So when you think about what's in the bubble, when you think about what's in the bubble when water's boiling, okay? Everybody wants to think it's just an air bubble. But it's steam. It's H2O. Okay? It's just because it's hottest at the bottom, because that's where it's attached, and that's where the flame or the coil is touching it. So the water gets super hot at the bottom, eventually separates from one another, breaks all the hydrogen bonds, forms the bubble, so it's water vapor inside that bubble. And then when it hits the cold air, it actually recondenses back, which is why we see it. It's the steam. Okay? And so it's the hydrogen bonds right here. This is actual AP test right here. This is the question on this.
Mr. Hobbs, does chemistry have, like, when we have to justify it the same way physics does? Are they going to be like the physics ones?
It's going to be just like the ones I just gave you. Most of the questions I gave you are modified AP questions.
Because Kramer's been doing, like, on the test, and giving us, like, one home run. And it's like, you have to design an experiment.
Oh, no. We generally don't have to do that.
Okay.
What else did I have? Okay.
No, I need my phone.
I go on top. I put this on top. Four staples.
Okay. Let's get this sheet out. Let's get this one. And somebody go next door and get Ava, please. Yeah. Somebody go get Ava.
Jen, just when you
Okay, let's get this sheet out. Shoot, I'm in. Oh, well.
AP chemistry review sheet?
Yes, AP Chemistry Review.
Try to hold like this. Just stuff that's in a folder, in my folder deck. This one? I already did this one. I'm not sure. This one?
Yes.
I did it. Yeah, I studied for that. I didn't done that.
Should we give an intro to your video?
So if we're looking at this right here, we talked about it briefly. We talked about how to do this briefly. So we're given, refocus now, we're given 17 grams of silver nitrate. Okay? 17 grams of silver nitrate. And 100 milliliters of 0.4 molar. So we have a balanced equation. 2 silver nitrate plus potassium chromate. Okay, ladies. Okay, so there's my given. All right. 10 minutes. 15 minutes. 15.
We get it. I learned it all. Like the line is going out the door.
We were just early one week. I don't know why, but no one else is out.
But we get there so late now.
We're supposed to get out at 12:20. Because we gotta be in there at 12:25.
4:30. Sure is. All right. 10 minutes. Okay. Yeah. All right. Let's get this one problem. So if we're given both of this information, what type of problem does this make it? Okay. Hey, there's just here. Come on. Come on. Hey, back row. And it's not Anthony. Okay. Just making sure. Okay. If we're given both pieces of information, both givens, what do we have to do? Find limiting reactant. How do we do that? First step is always. Okay, so Morgan, what? How do I convert 17 grams to moles? The molar mass, which is 170 grams. So that's going to equal 0.1 moles. Then I have, how do I convert this to moles? So this one's actually easier because you don't have to calculate it. So this is going to come out to equal 0.04 moles. 0.0 moles of not AgNO3. Now, so does that make this one automatically the limiting reactant? Okay? So, which one's my limiting reactant? Yeah, this is my smaller one. So this is the limiting reactant. So that's the one I want to use. So the question is, how many grams of this? Now it's just like any other stoichiometry problem, because now we can just start with moles. 0.0400 moles times 1 mole over 1 mole, because that's my limiting reactant, times the molar mass of this, which was that, 275? What is it? Is it more? So it's 216 plus 52 is 268 plus 64 is 272, 332. Okay, so then what? That's right. Then what you're given. Okay, so 0.04 times 332 is equal to 8, 12, carry 1, 13, 13.28. Okay, now, the whole point, the main thing I want you to get out of this, okay, the main thing I want you to get out of this is, oh, it did turn, it did follow me, okay? The main thing I want you to get out of this is how to calculate the limiting reactant from solution. You still convert to moles. Y'all, come on back. If it followed me around, okay? You guys, just like the crazy people on Sports Center behind the okay? So, if you have a solution volume stoichiometry problem, you want to convert it to moles using the molarity, then do everything else the same. Now, the other problem that we were working on yesterday Here's another problem. What is the Cl minus concentration when 25 milliliters of 0.15 molar NaCl is mixed with 30 milliliters of 0.20 molar CaCl2? Okay, ladies. I know. All right. Y'all, I know it's been a long day, but we haven't been very intense today. We got 5 minutes of intensity. How do we do this? Okay? What does, first off, the brackets, remember the brackets mean molarity. In terms of molarity, okay? That's going to equal moles of Cl minus over liters of solution. Okay? So, once we mix them together, what's my liters of solution going to be? 55 milliliters, which is going to be 0.055 liters. So I know that just from adding it together. That's 25 milliliters plus 30 milliliters. So what do I need to know? Total moles of chloride. Well, the chloride's coming from two sources. It's coming from the NaCl. It's coming from the CaCl2. So we got to figure out moles from each one, add them together, and then put it into here. So how do we find moles? Okay? Remember, moles is going to equal molarity times volume. Seriously. Okay. Shh. Out loud. Molarity is 0.15 times the volume, 0.025. So that's going to give me moles of Cl minus from the NaCl. And what's that going to equal? All right, I'm trusting y'all that you're right. So that's from the NaCl. So what do I do for the CaCl2? It's going to equal the molarity, 0.2 molar, times 0.030 liters. And that's going to come out to 0.006. But what do I need to do to that? Why double it? Because it's going to be 2 chlorides because it's CCl2. So it's going to be times 2 moles over 1. So it's going to equal 0.0120 moles of Cl minus. So my total moles is going to equal 0.00375 plus 0.012 is going to equal 0.01575. So what do I do with that? And so the chloride ion equals chloride ion equals Okay, so that would be the chloride ion concentration in solution. Now we're going to need to be able to do this when we do later problems dealing with KSP equilibrium, first thing, second semester. We're always going to be able to know how to do the total ion concentration. You also will need to be able to do this for next week on the test. Okay?
How late this week are we doing this test?
I don't know.